So section 10.4 is on the hyperbola, which is another one of our conic sections. And this is the shape that we get from slicing all the way through both of those cones and looking at that cross section. So we'll end up with two different pieces of this graph. So I'll just jump right in and give you the definition and show you what this looks like. We'll go over all the important terminology. I'll put up the equations and then we'll go over some examples. So a hyperbola is the collection of all points whose difference of distances from 2 points called the foci is constant. Okay, so a hyperbola is a collection of all points whose difference of distances from 2 points called the foci is constant. Now, this definition is almost identical to the definition of the ellipse. The only change here is on the ellipse. The ellipse was a collection of all points whose sum of distances from 2 points is constant. Okay, so those equations are going to look pretty similar. There's two ways our hyperbola can be oriented, either horizontally or vertically. So let me show you what a hyperbola looks like if it is oriented horizontally. We have these two axes, and I'll give you all the terminology in just a second. And what we're going to have here is we're actually going to have some oblique asymptotes. And our hyperbola has two pieces to it. So it's going to follow these oblique asymptotes along the left and along the right. If we have a hyperbola that's oriented vertically, we'll have these oblique asymptotes. And we're going to have two pieces of our graph that follow those oblique asymptotes. It'll look something like this. Okay, so now let's label all of the important things. I'll give you our new terminology, and we'll talk about A, B, and C, the distances from our center to our vertices, the distance to our foci, etc. All right, so our terminology in this section is different than in the last section. The first one we have is the transverse axis. The transverse axis is the line through the center containing the foci. Okay, so this is our center. This is our center. On this picture, our foci actually sit in here inside each of these parts of our curve. Okay, so here where it's oriented vertically, our foci sit inside these curves like this. Okay, so on this picture, here's our transverse axis. We would say if it's oriented horizontally, the transverse axis is on or parallel to the x-axis. Here where it's oriented vertically, the transverse axis is on or parallel to the y-axis. The other axis through the center is called the conjugate axis. So the conjugate axis is the line that's perpendicular to the transverse axis through the center. Okay, so this would be our conjugate axis, and this would be your conjugate axis. So notice our terminology here is different than when we had the ellipse in the last section. So ellipse, we had major axis and minor axis. Here we have transverse axis and conjugate axis. So sort of the same idea, but just new terms for this new shape. Okay, our vertices are our points of intersection with the transverse axis. So here's our vertices, and here are our vertices. So the vertices and foci, right, these are the same words we saw in the previous section. So those vertices are these points of intersection. The vertices on ellipse are also the points of intersection with the major axis. Okay, our next new term is branch. Branch is what we call each part of the curve. So for example, in this one where it's oriented horizontally, we would refer to this part of the curve, the left branch. This would be the right branch. Up here, this is the upper branch, lower branch. Okay, so we have two branches, two branches. Okay, so each part of the curve we just call the branch. So left branch, right branch, upper branch, lower branch, top branch, bottom branch, anything like that. Now A, B, and C, these distances are going to be similar to what we saw in our ellipse. So let's write those out and we'll draw them on our picture here. So A is our distance from the center to the vertices. Now notice that's the same. When we did the ellipse, A was our distance from the center to our vertices. And usually in math, we like to try and keep these things the same as best we can. So let's draw A on our picture. So our distance from our center to our vertices. From our center to our vertices, this is A, this is A. B, let's come back to that in just a second. C is going to be the same as we had with our ellipse. C is our distance from our center to our foci. So our distance from our center to our foci, that's C. That has not changed. If you go back to the first picture on the ellipse from 10.3, A and C had the exact same definition. Now B is going to be a little bit different. So for our ellipse, we had this minor axis and our ellipse intersected the minor axis. So we had points of intersection with the minor axis. Here we have this labeled as the conjugate axis. And if we look at this, neither of our branches actually cross the conjugate axis. So B technically isn't our distance from the center to points of intersection with this other axis here. Okay, so how is B going to come into play? B is going to come into play when we're finding the equations of these oblique asymptotes. So remember these oblique asymptotes from Math 126, they're just lines that our graph follows as we go out to positive and negative infinity. And oblique means they're not horizontal and they're not vertical. Okay, so B is going to come into play when we find the equation of our oblique asymptotes. And it turns out if we were to draw a little, well, let me do this with yellow in here. If we were to draw a little square in here, this distance is going to be B. So our oblique asymptotes are going to go through a rectangle here that has a width from the center out to the side of A and a height of B. So if we did the same thing here, we drew a rectangle in here, our oblique asymptotes would go right through the corners of this rectangle, and this distance would be B. That yellow doesn't show up very well at all. Let me see. And the oblique asymptotes will go right through the corners. And I'll show you how this works. This one, I'm sorry, my drawing's a little off, but these should go right through the corners. All right, so there's all of our new terms. We'll go ahead and just jump right in. I'll give you the equation like I did before for the ellipse, and then we'll do, I think I have 3 examples of graphing as well. Any questions so far? Okay. So we're gonna have 2 different equations, one for where the hyperbola is oriented horizontally, the transverse axis is on or parallel to the x-axis, and then one for where it's oriented vertically. Oh, I can put this all on one page. Okay, so if we have a hyperbola with center HK, we have 2 different scenarios, one where our transverse axis is parallel to the x-axis, one where the transverse axis is parallel to the y-axis. I'll give you guys a couple minutes to jot these down and then we'll talk about them. So of course, as we've done all semester, if the proof is instructive and simple, I like to give it to you. I do not think that the proof here is very simple, so I'm not going to go over the proof. However, I think the proof is interesting. So if you're interested in this after class, you can Google proof of hyperbola equation, proof of hyperbola formula, something like that, and watch something on Google with how these formulas are derived. Okay, so the first thing you should notice in both of these formulas is that because our definition of hyperbola had difference instead of sum, we have a subtraction sign in the middle here instead of an addition sign that we saw on the ellipse. Okay, the next difference we notice is that this one's written x minus h and this one's written y minus, or I'm sorry, x minus h and then minus y minus k. Here's y minus k minus x minus h. So for the hyperbola, what determines where our transverse axis is what variable occurs first. So here where the x occurs first, that determines that our transverse axis is parallel to the x-axis. Here our y occurs first. That's what determines that our transverse axis is parallel to the y-axis. Okay, so this is very different than the ellipse. For our ellipse to figure out where the major and minor axis was, we looked at the denominators, figured out which one was bigger. Here this is different. X occurs first. That means our transverse axis is parallel to the x-axis. Y occurs first. That means our transverse axis is parallel to the y-axis. Okay, the next thing is that where A, B, and C are, right? So here A squared is always going to be the variable that occurs, or underneath the variable that occurs first. So we're always going to have A first and then B second. In our equation of our ellipse, A squared had to be the larger denominator. Okay, that is not the case here. It's always going to be A squared under the first and B squared under the second. Okay, C squared is equal to A squared plus B squared. Our ellipse, we had C squared was equal to A squared minus B squared. So these are a little bit different based on the derivation of the formula. Again, anyone who's interested, I would encourage to look this up. Okay, so our foci are a distance of C away, so we still add and subtract C to our x coordinate here. Our vertices are a distance of A away, so we still add and subtract A to our x coordinates. The new thing here is our asymptotes, right? We have these oblique asymptotes. This is point slope form for a line. So HK is the center, right? So that means here's our point, HK. So point slope form, HK. And this is saying that our slope of our asymptotes are plus and minus B over A. Down here it's plus or minus A over B. So what's the difference? If we look at our picture, first up we have the hyperbola that's oriented horizontally, right? So that would be transverse axis parallel to the x-axis. We can see that our rise over run, the rise here is going to be B, the run is going to be A. And then this asymptote has a rise of negative B over A. So that makes our slope of these asymptotes B over A. Algebraically, the way we can find those is when we're finding our oblique asymptotes, that's our end behavior. So we'd start by solving for y. So when we solve for y, we'd move this term to the right. That would put the a squared in the bottom. We'd multiply both sides by b squared. That puts our b squared in the top. To solve for y, we take the square root of both sides. That would give us the plus or minus b over a. Okay, so that's actually where it comes from algebraically. Okay, let's look at our asymptotes down here for when our transverse axis is parallel to the y-axis. If we look at this picture, our rise is A, our run is B, so we assume that the slope here should be A over B, and we have plus or minus, so here's one with a positive slope, and here's one with a negative slope of A over B. Algebraically, where this comes from, again, is by solving for y, right? That's our end behavior. So we move the x term to the right. That puts the b squared in the denominator. Multiply both sides by a squared. We'd end up with a squared over b squared. Solving for y, we take the square root of both sides. That's where we get this plus or minus a over b. All right, any questions so far? Oh, and down here, of course, when our transverse axis is parallel to the y-axis, to get to the foci and vertices, we're adding and subtracting these values on the y coordinates. All right, any questions so far? Okay, so we'll just go ahead and graph a few of these. So let's graph the hyperbola. And I have 4x squared minus y squared is equal to 144. Okay, so the first thing we want to do is get this into standard form. So to get it into standard form, we saw that all those equations had a 1 on the right side. So I'm doing these examples on purpose so you can think about what should your first step be. We need to get a 1 over here, so our first step here is we'll divide all of our terms by 144. All right, so 4 over 144, these both have a common factor of 4. 4 goes into 4 one time and into 144 36 times. So that gives us x squared over 36 minus y squared over 144 is equal to, and on the right side we have a 1. Okay, so first thing we notice, we have a subtraction sign in the middle. That means it's a hyperbola and not an ellipse. If we had an addition sign in the middle, it would be an ellipse. Hyperbola and ellipse both have a 1 on the right side in standard form. All right, the first thing we want to do is figure out where our transverse axis is. Remember, these terms are different. So for ellipse, we had major axis. Here we have transverse axis. So our foci and our vertices are on this transverse axis. So the transverse axis is on or parallel to. The way we determine this is different than for the ellipse. Whatever variable occurs first, here we have the x occurring first, that tells us where our transverse axis is. So our transverse axis is going to be on or parallel to the x-axis. The next thing we want to do is list out our center, our foci, our vertices, and then for this, our asymptotes. All right, our center, we have x minus h squared and y minus k squared. So here we haven't subtracted or added anything. Here we haven't subtracted or added anything. So our center is at the origin, 0, 0. And again, I've picked kind of the simplest example to go first. The other examples we'll do where our center is off the origin. To get to our foci, our vertices, and our asymptotes, we're going to need to know our variables a, b, and c. So let's list those out. Now, this is different than the ellipse. Different than the ellipse. We always, always, always list these out in alphabetical order from left to right. So this is a squared and this is b squared. Regardless of what variable is in the numerator, these are always going to be in order, a squared and b squared. Okay, for the ellipse, the larger one was a squared. Hyperbola here is different. Always left to right, a squared, b squared. So we get that a squared is 36. Which means a is 6. That is our distance to the vertices. We have that b squared is 144. That means that b is 12. We are going to need this to come up with our oblique asymptotes. We have that c squared is equal to a squared plus b squared. So c squared is, a squared was 36, b squared was 144. So we get that c squared is 180. So 180 is 36 times 5. So, oh, I'm sorry, I have one more step here. C is the square root of 180. 180 is 36 times 5, so we get that c is 6 root 5. This is our distance to our foci. All right. So our transverse axis is on or parallel to the x-axis. That means to find these foci and vertices, we are going to be adding and subtracting on the x-coordinate, So we're starting at 0 and 0. To get to our foci, we need to go a distance of 6 root 5 on the x-coordinate. So that puts our foci at negative 6 root 5, comma 0, and positive 6 root 5, comma 0. To get to our vertices, we want to go a distance of 6 along that x-coordinate. So we'll go negative 6, comma 0, and positive 6, comma 0. Our asymptotes. These are of the form y minus k is equal to plus or minus b over a times x minus h. So our center here is hk. So we're plugging in, this is point slope form of a line. We're plugging in a point and we're plugging in our slope. So I have y minus 0 is equal to plus or minus b is 12, a is 6, and then x minus 0. So let's work this out a little bit. I get y is equal to plus or minus 12 over 6 is 2, x. So our asymptotes are y is equal to 2x and y is equal to negative 2x. The last thing we'll do is put all this together into a beautiful graph of a hyperbola. So I need to start on a new page here. So I'll give you guys just a second to make sure you got all this down before I move to a new blank page. Okay. So as always, I would encourage you to try and graph these by hand before you jump to that electronic graphing tool on your homework, especially those of you that are moving on to higher math classes. It is important that you know how to do these by hand. All right. So I am going to label what we know is like to figure out how much I need to put on here is I need my rise over run to be 12 over 6. So on the y coordinates, I need to get up to positive 12 and down to negative 12. And then on my foci, I need to get out to 6 root 5. And that's about 13 point something. So I'm going to count by twos here since we got a lot to travel. So 2, 4, 6, 8, 10, 12, negative 2, negative 4, negative 6, negative 8, negative 10, negative 12. Okay, so our center is 0, 0, HK. If you would like to label that with a C for center, you certainly can. The next thing we know is our transverse axis is parallel to the x-axis. It's actually on the x-axis here. So to get to our foci and our vertices, we're going to be moving on that x-coordinate. We figured out that our distance to our vertices was 6. So if we go to the left and to the right, 6, those should be our vertices. Now let's check our points. We had that our points when we worked this out were negative 6, 0 and positive 6, 0. So that matches exactly. The next thing we had was our distance to our foci was 6 root 5. Okay, so again, when we want to approximate this, we should ask ourselves, what is this close to? 180, this is close to 169. We know square root of 169 is 13. So we need to go 13 to the 13 point something to the left and to the right. It's going to be a little bit bigger than that. So our foci are going to be out here and out here, foci, foci. The next thing we want to do is get those oblique asymptotes in there. Okay, so here's the box method of putting up those oblique asymptotes. There's two ways of doing this. One way is we know what the equations are. We can graph these lines. I like the box method because it uses A and B. So we know that A is our distance from our center to our vertices. A was 6. What I want to do is create a box whose height is B. So B was 12. Okay, so what I'm going to do is make this box in all 4 directions like this. Then I'm going to do the same box over here, the same box over here, and the same box down here. Our oblique asymptotes will always, always, always go right through the corners of this box and through the center. Now this should match, right? The slope of this line is B over A here, and the slope of this line is negative B over A, which is exactly what we did when we calced these out. So this one happens to be y is equal to 2x, and this one is our y is equal to negative 2x. The last thing we want to do is draw on our left branch and our right branch. They should hit these vertices and then follow these asymptotes. So it's going to look like this. Our foci should sit inside these branches. Okay, so we have a few more examples of graphing a hyperbola to do in section 10.4. So let's just jump right on in. So next example here, let's graph y plus 4 squared over 9 minus x minus 2 squared over 16 is equal to 1. So the first thing we should check when we're graphing hyperbola or even ellipse from the last section is that our equation is in the standard form. So standard form means factored, a 1 on the right side, so it looks good. Later on in your math career, should you be given an equation like this and you have to determine yourself whether it's an ellipse or a hyperbola, remember the main difference is the hyperbola here has a subtraction sign and ellipse has an addition sign. Okay, so that's how we determine which one we should be graphing. All right, the first thing we should determine is where the transverse axis is. So remember, the transverse axis is the line through the center that contains the foci and the vertices. So the transverse axis is going to be on or parallel to. And we want to determine if it's on or parallel to the x-axis or the y-axis. And the way we determine that for the hyperbola is based on what variable occurs first. So this is very different than the ellipse, where we determine where the major and minor axis are. Here in our equation, whatever variable occurs first, that tells us where the transverse axis is. So here the transverse axis is going to be on or parallel to the y-axis. The next thing we should do is determine the center, the foci, the vertices, and our asymptotes. Okay, so our center is given by h comma k. And the way we find the x coordinate of the center, this factorization is always x minus h squared. So x minus h, that means the x coordinate of the center is 2. Here, this is y minus k, so y minus -4 makes this y coordinate -4. Okay, so the important thing to remember here is they need to be of opposite signs. So this is x minus h and y minus k. So here we should use -4. The next thing we got to do is list out the foci, the vertices, and the asymptotes. And in order to do those things, we need to find A, B, and C are variables. So let's work on that, and then we'll list out the foci, the vertices, and the asymptotes. All right, so this is different than the ellipse. When we're working with hyperbola, from left to right in alphabetical order, we list these out as a squared and b squared. This is different. Remember when we did the ellipse, the larger denominator was always a squared. That is different for the hyperbola. And we go from left to right in alphabetical order. All right, so we have a squared is 9, which means a is equal to 3. We got b squared is equal to 16, which means b is equal to 4. And then we have c squared is equal to a squared plus b squared. So c squared is equal to 9 plus 16. So c squared is equal to 25, so c is 5. All right, so let's remember from last class and also from our ellipse section, A and C are the same. So A is our distance from our center to our vertices. C is our distance from our center to the foci. And then B is going to come into play here when we find our oblique asymptotes. Okay, so the next thing we'll do is we'll find our foci. Remember, this is plural for focus. So what we want to take a look at is, because the transverse axis is on or parallel to the y-axis, that means when we are looking for the foci or the vertices, we are moving parallel to the y-axis. We're moving on that y coordinate. So what I like to do is start with the center, which is 2, -4, and leave a blank on the y coordinate here because we're moving along the parallel to the y-axis. So let's see, we got 2, -4, we need to do 2 here. We need to go plus or minus. And to get to our foci, that's a distance of 5. So here I'm going to go -5, and here I'm going to go +5. So that gives me 2, -9, and 2, +1. All right, let's find our vertices. So again, these foci and the vertices, we're moving along parallel to the y-axis. So I'm going to start with my center, 2, -4. And I need to go plus or minus a distance of a. So we'll go -a and +a. That gives me 2, -7 and 2, -1. The next thing we'll do is find our asymptotes. And to find our asymptotes, we are using point slope form, and we know one point on our asymptote is h comma k. And then if we were to evaluate the end behavior of this, we're going to get plus or minus a over b for our slope of our oblique asymptotes. Okay, so this is just point slope form. We're filling in a point, HK, which is our center. We know that the asymptotes go through the center. And then this slope comes from the end behavior when we solve for y here. All right, so let's fill in. K up here was -4. A was 3, B was 4, and we have that H was 2. Now pay attention on your homework. You might be able to, I think some of them are multiple choice there, or you can leave it in this form. Usually what we like to do for lines, anytime we're working with lines, we like to have them in slope-intercept form. So if you need to put these in slope-intercept form, what you would do is do two separate equations, one with +3/4, one with -3/4, and multiply this out and then solve for y. For the sake of time here, I'll tell you how these work out. You should get y is equal to 3/4 x minus 11/2, and y is equal to -3/4 x minus 5/2. Any questions so far? Okay, so now we have all the information we need to know to graph this. So I'll give you guys just a second here to get this all copied down, and then we'll start on a fresh page and we'll graph this. Okay, so when we're doing this graph by hand, and as always, I would encourage you to do it by hand, you want to figure out what you need to put on your x-axis and what you need to put on your y-axis. So if we look at our y coordinates here, our y coordinates go from -9 up to +1. And then the x coordinates of all these things are at 2. But we're going to also use this box method to put in these asymptotes. So since b is 4, I want to make sure I go 4 in either direction from this x value. Okay, so my y values, I'm going to go from -9 to 1. And then for the x values, I'm starting at 2, and I want to go 4 to the left and 4 to the right. So I'll make sure to put all of that on my graph. Okay, so the first thing we have is that our center was at the point 2, -4. Okay, then we had that our foci were a distance of 5 away, up and down. Oh, and if you want to label this C for center, if that helps you, you can do that. Our foci were 5 up and 5 down. So 5 up, there's a foci, and 5 down, there's another one. And our vertices were 3 up and 3 down. So here's our vertices. Okay, the next thing we have is these asymptotes. Now, there's two ways of doing this. The first way of doing these asymptotes is by looking at these equations of the lines in slope-intercept form. Okay, the way that I think is a little bit easier is by using this box method. So I'm going to show you the box method. Of course, you're welcome to graph these by hand. In order to graph these by hand, I'd start with the y-intercepts and then draw one more point using the slope and then fill in the lines. Okay, what I like is we know our distance from the center to the vertices. This is a distance of A, which was 3. Okay, so B comes into play with our oblique asymptotes, right? We know our slope was A over B. So what I'm going to do is go a distance of B, which was 4, over and form a box. I'm going to do this in all 4 directions. So here's 4 over. Here's A down and B across. Now, it just so happens that our oblique asymptotes are going to go through the center and they will go through the corners of our box. So our first oblique asymptote should go right through here. And our second oblique asymptote should go right through here. All right, now let's check this with our slope-intercept form and make sure we got them correct. So our line with the positive slope, 3/4, this has a slope of 3/4, so up A, which is 3/4. And the y-intercept was -11/2, which is -5/1/2. We nailed that one. Our oblique asymptote with the negative slope, that had a slope of -3/4, so down 3/4, perfect. And the y-intercept was -2.5, so nailed that one too. Great. So the last thing we want to do is draw in our upper and lower branch. So our branches should follow these asymptotes and hit these vertices. So it's going to look something like this and like this. Remember, the foci sit inside these branches. The branches hit the vertices. Any questions on that one? All right, we will do one more. Okay, next one. Let's graph x squared minus 4y squared minus 8x minus 24y minus 36 is equal to 0. Okay, so let's graph x squared minus 4y squared minus 8x minus 24y minus 36 is equal to 0. All right, so what we want to do is start by getting this in standard form. So standard form meaning that those x terms and those y terms are factored and we have a 1 on the right side. Okay, so first thing we need to do is factor. I'm going to factor this by completing the square. I'll give you a little bit of review on factoring by completing the square. You should have learned how to do this in your Math 096 class, however. So if you need a little bit more review, make sure you either look at your old notes or Google factoring by completing the square. But I'll tell you how to do it. So the first thing we want to do is write our x terms together. So I'm going to write x squared minus 8x. To complete the square, we're going to need to add a blank. So I'm going to put a plus a blank here. Next up, I want to write my y terms, and I'm going to factor out this -4 in front of the y squared. So I'm going to write -4. My y term here was y squared. And then if I pull out -4 from -24, that leaves me with plus 6y. Now I'm going to complete the square, so I'm going to put plus a blank here. On the right side, I want to take this constant and move it to the right, so that makes it positive 36. And then I need to remember whatever I add here on this blank, I need to add that over here. And whatever I add here, I'm actually adding -4 times this, so I need to do -4 times this blank. Okay, next up, in order to complete this factorization, we're completing the square. Our process is always the same. Our process is always divide by 2 and square. Our process is always divide by 2 and square. So we take this middle number, this -8, we divide by 2 and square. So -8 divided by 2 is -4. -4 squared is 16. So if I add 16 here, I have to add 16 here. Okay, here, middle term was a 6. 6 divided by 2 is 3. 3 squared is 9, so I'm adding the 9 here, so I'll have to add that over here. Our next step is to do the factorization. So x squared minus 8x plus 16, this factors as x minus 4 squared. There's 2 ways to come up with this factorization. The first way is to ask yourself, what times itself gives you positive 16, but added to itself gives you -8. So -4 times -4 is positive 16, or -4 plus -4 is -8. The shorter way is if we write out these steps, this number goes right in there. So that means using our shortcut here, this number goes right in there. On the right side, I got 36 plus 16 minus 36. So 36 minus 36, those are going to cancel out, and I'm just left with 16. In order to get this in standard form, we need a 1 on the right side. So our next step here is to divide all of our terms by 16. That gives us x minus 4 squared over 16 minus 4 and 16. They both have a common factor of 4. So this becomes y plus 3 squared over 4 is equal to 1. So all that work just to get to the start of this problem, really. Okay, so again, what we would want to do is identify that this is a hyperbola and not an ellipse. The difference between the hyperbola and the ellipse is, of course, this sign in the middle. Here we have a subtraction sign, so that's a hyperbola. If we had an addition sign, then we're looking at an ellipse. The first thing we should do is figure out where our transverse axis is. Okay, so our transverse axis is going to be on or parallel to whatever of our variables occur first. This is very different from the ellipse. So for the hyperbola, here we just look for what is first, and we have the x first, so the transverse axis is parallel to the x-axis. The next thing we want to do, let's list out our center, HK. So our equation was x minus h, so that means h is 4, and y minus k, so k is going to be -3. The next thing we need to do is list out our foci, our vertices, and our asymptotes. So in order to do that, we need to find A, B, and C. So remember, on a hyperbola, we're going from left to right alphabetically. So this is A squared, and this is B squared. Remember that the ellipse is different. The ellipse, whatever denominator is larger, that gets to be A squared, and that also determines where our major axis is. Okay, so A squared is 16, which means A is 4. B squared is 4, which means B is 2. And then C squared is equal to A squared plus B squared. So C squared is 16 plus 4. So C squared is 20, which means C is the square root of 20. Here we have a perfect square of 4, so we pull that out as a 2, so this becomes 2 root 5. All right, next up, let's list out our foci, our vertices, and our asymptotes. So our foci, what I want to do is start at my center for -3. And, oh, I forgot to write here. Let me just remind myself. A is our distance to our vertices. C is our distance to our foci. And then B is going to come into play when we look at those oblique asymptotes. Okay, so to get to our foci, we need to go a distance of C. And since our transverse axis is on or parallel to the x-axis, we're moving along that x coordinate. So what I like to do is start with my center for -3 and leave myself some room on this x coordinate to fill in plus and minus c. So we want to go 2 root 5 in either direction. So -2 root 5 plus 2 root 5. Next up, let's find our vertices. So again, we're starting with our center, and since our transverse axis is parallel to the x-axis, we're going to move along that x coordinate. So to get to our vertices, we need to go a distance of A, which is 4. So I'm going to subtract 4 and add 4. That gives me 4 minus 4 is 0, and 4 plus 4 is 8. The next thing to do is find our asymptotes. I have run out of room on this paper, so I'm going to start on a new page. I'll give you guys just a second to get caught up. Okay, Okay, so to find our asymptotes, we're using point slope form, so that's y minus k is equal to plus or minus. And then for where the transverse axis is parallel to the x-axis, we're using b over a times x minus h. Okay, so we know that our asymptotes have a slope of b over a, plus and minus b over a, and then hk, that's our center. The asymptotes have to run through our center. So now we're going to plug in h and k and b and a. So I get y minus k was -3, plus or minus b is 2, a is 4, and h was 4. So we get y plus 3 is equal to plus or minus 1/2 of x minus 4. Usually when we have lines, we like to write them in slope-intercept form. So to get them there, we would break this up into 2 steps. We'd have one asymptote with slope plus 1/2, one asymptote with slope minus 1/2, and then multiply this out and solve for y. That gives us y is equal to 1/2 x minus 5, and y is equal to -1/2 x minus 1. All right, we have everything we need to graph this bad boy now, so let's do it. Again, I would highly suggest you try to do this by hand before using the graphing tool. So we look on those x coordinates of our foci and our vertices. We need to go from -9 out to 1, so I'll make sure to put that on my x-axis. And then for the y coordinates, we need to go a distance of b up and down from the center. So I'll make sure to get all of that on there. Okay, so first up, our center was 2, -4. If it helps you, you can certainly mark that with a C for the center. Next up, we found that our foci were a distance of 2√5 in either direction. Okay, so if you're doing this by hand, the way we can picture where these foci are going to be is by looking at that 2√5 was a square root of 20. So square root of 20, that's between 16 and 25. Those are the perfect squares. So that means that square root of 20 is going to be between 4 and 5. So I want to go about 4 point something to the left. So 1, 2, 3, 4 point something. And 4 point something this way. 1, 2, 3, 4 point something. Did I mess this up somehow? 0, -8, foci, 4√2. Oh, I'm so sorry. I'm so sorry. I somehow was looking at some other point. Let me backtrack for just 1 second. Our center is 4, -3. 4, -3. I have no idea what I was looking at there. I'm so sorry. Okay. So our center is 4, -3. I'm looking at some other point on here. I apologize. So here's our center at 4, -3. Sorry. All right, so our foci is a distance of 2√5, which we determined was 4 point something in either direction. That looks way better. Okay, so 4 point something, so there's 4 point something and 4 point something. Okay, that looks better. I'm so sorry. Next one, our vertices were a distance of 4 in either direction. So 4 and 4. Okay, that looks better. All right, so to get our asymptotes in there, we can either use the slope-intercept form to get those lines, or I like this box method. So we know our distance from C, from our center out to our vertices is a distance of A. So what we're gonna do is go up and down a distance of B. So B was 2. So we can go up 2 and draw a box. We can go down 2 and draw a box. And we'll go in the other directions as well. Okay, so now we know that our asymptotes have to go right through the center and through the corners of the box. And then the other one right through the other corners and through the center. Now let's make sure that this matches the equations we had up here. So the first one had a slope of positive 1/2, so that's up to over 4, so that's the same as 1/2. And our y-intercept was -5, so nailed that. The other one had a slope of -1/2 and a y-intercept of -1, nailed that. Okay, so our left branch and our right branch, they need to follow these asymptotes, and remember the branches hit the vertices. So the foci sit inside, and these branches hit the vertices.